Good afternoon, all. Let us start the session now. As you know, it's the last day and probably the last session, academic session, but we started 6 days back around, and today we have a very good talk on cosmological puzzles in the multi-messenger era by Professor Shankaranarayanan. Professor Shankaranarayanan obtained his PhD degree from a well-known institute, Ayuka Pune, and after his PhD degree, for after postdoctoral work, which was at ICTP Trieste and Albert Einstein Institute of Germany, then he worked as a Marie Curie Fellow at Institute of Cosmology and Gravitation at Portsmouth. Between 2009 to 2017, he was a faculty member at the School of Physics, ISER, Thiruvananthapuram. Then he joined Department of Physics at IIT Bombay in July 2017, and where he is currently working as a professor. His research areas are mainly the black holes, cosmology, and quantum gravity. He will be talking to us for almost 50 minutes on cosmological puzzles in the multi-messenger area. I request you, sir, to start your presentation. We'll be having presentation up to 50 minutes, and then 10 minutes can be assigned to question answers.
Okay. Thank you very much for the introduction, and thank you very much for inviting me to give a kind of an overview talk for this astronomical calculations with Python audience. So as I understand, many of you have actually undergone many of these data analysis and with astronomy, and various aspects of talks were being given in the last 2-3 days. So what I wanted to start with is to continue that same thing which you have been hearing for the last 2.5 days. And then I will take on to what are the problems which we are facing currently, and how we think in the next 15 to 20 years, we might actually have a better understanding of this. So what I talked to both Professor Shetty and Dr. Bole. I will take questions after 15-20 minutes, and then if there are, and then I can do this every 15-20 minutes, so that then we can finish the talk in 1 hour. So I also want to wish everybody a happy new year. So what we are currently witnessing is something extraordinary. See, we have been hearing, we know that we are hearing the hummings from the universe, from galaxies, stars, and particles, carrying a lot of cosmic riddles. Okay, and all these riddles were actually, we have been trying to solve for the last 400 years. Once Galileo picked up the telescope and made a telescope, and only with one source, which is basically electromagnetic or light for most of the part. Now we are in the era of what is called the multi-messenger era. You must have heard this word, but I'm just going to explain it. So this basically tells that we are not just going to rely on electromagnetic fields, but electromagnetic waves, but we are also going to get information about the cosmology from gravitational waves, neutrinos, high energy particles, as of course, electromagnetic signals. So now we are going to try to compress all these data and try to see what story we can actually come up with for the universe, and what the story the universe is trying to tell us. So I also will look at what are the tantalizing puzzles which cosmology has posed us the last 20 years or so, and what people are trying to make out of it, and what are the ways in which we can try to understand by using the next generation of telescopes in various of these things. So that's basically what I wanted to start with. So I wanted to put this slide because even though many of you may not understand everything, but I just wanted to put this, how our understanding of the universe has been evolving for a long time. In the sense, we didn't know anything about the universe for 100 years. But if you look at it, in 1970s, it's not just, it's only 50 years ago, we thought that our understanding is that the entire universe was made up of two parts. One is basically what is called the ordinary visible matter. Visible matter, when I say, is basically photons, particles, hydrogen, everything. Because hydrogen is maximum, most of the maximum. So I'm going to call it as hydrogen, and rest of it is ordinary matter. That's how we thought about it in 1970s. And this dark matter was not nothing. It's just that we are not able to see it. It is just ordinary visible matter, but except that we don't see it. But in 80s, it changed because we had a lot of other experiments and other observations. And it basically said that now this is not just dark matter, any ordinary matter, but it's an exotic dark matter. Okay, that's what these indicate. But in 1990s, when there is a lot of other supernova and other CMB measurements came up, then they said, no, we are not living in a universe where it's just only matter, but we also have what is called the dark energy. And then 27% of that only contributes to the exotic dark matter, and the rest of it is very, very small amount, basically. And this is what we actually, our current understanding of the universe looks like. Okay. Now, please understand, in the last 50 years, that our understanding of the universe has dramatically changed, but we have a lot of things which we don't understand. Okay. So if you want to ask a question, how did we reach? So basically, we thought that everything, we only thought that the only solar system or galaxy is the only universe in this planet for the last, for more than 5,000, 6,000 years. But suddenly we now look at a universe which is very, very big. And not only that, we also think that only 5% of the matter which we kind of see it in the earth, which is what basically made up of hydrogen, helium, and things like that. And that is only composition of only 5%, but rest of it is something which we don't know. Fine. So the question is, how did we reach? Okay. As I started, we had one eye, which I will call it as an eye, which is basically electromagnetic waves. And that is basically what Galileo made a telescope 450 years ago. And which is basically the visible light. And that is here. It is here. And then it was expanded to all other electromagnetic spectrum after the Maxwell's famous equations. And people were figuring it out, all radio waves and other things. So it was basically all these things were there. And now we get information about the universe from the entire spectrum, starting from gamma rays, X-rays, ultraviolet, to very long wavelength radio waves. Okay. And how do they are all emitted by electrons, protons, and things like that. So they all carry energy. And these energy comes and hits us, and we detect it using a detector. And what do the detectors are? These detectors can depend on whether it is visible light or gamma rays or radio waves. And depending on it, will be different detectors will be there. And these detectors detect energy. And the energy or the luminosity, which is what I think you all must be knowing now. So the luminosity goes as inversely proportional to 1 over r squared. And this is important when I come back to when I discuss about the gravitational waves. And this is basically what we keep measuring. Once we have sophisticated instruments, which are all going up like James Webb Telescope or HST before, so that we will be able to get very precise measurements, and that's what we keep doing. Fine. Okay, so now how do we do it? So basically, we have a telescope. It could be it could be radio, it could be light, it could be anything else. So we have a very sophisticated instrument. So what do? We measure the stars. What are the absorption line spectrum? We also do the same thing for galaxies, clusters of galaxy, and many of them, when they pass through the intergalactic medium or the interstellar medium, then they will be absorbed by the low density gas which is there, and we get information about that, and the dust which is also there, which also blocks it. So we get a lot of these information about it. Okay. And this is basically what we thought that we had. So basically whatever we saw was basically light and matter basically emitting it. And we thought that, okay, we know that, and that is basically everything else. So the question is whether there is anything else out there, which is basically the question. Not in the question of extraterrestrial, but we are talking about galaxies and matter fields and stuff. So let us just go ahead and let us look at what do we know? What do we understand? So the first thing which people have been trying to see is basically look at the solar system and whether we understand solar system well. So we know that there are nine planets, and these planets go around the sun due to gravity. And we know that the mass of the sun is very, very large compared to all the masses put together of all the planets, right? Because so if I take the mass of the sun, which is given by m dot, and you take all the planets, sum over it, then this mass is much larger than this, because this is 10 power 33. This is anyway, the maximum is 10 power 30. So it is actually going to be of the order of 10 power 30. So there is 3 orders of magnitude different. Now you can ask the following question, what is the distance? So you take the radius of the sun and ask a question, what is the closest distance for the planet and the sun? So you know that the distance, the radius of the sun is much smaller than the distances between the planets and the sun. So then what people did is the simplest thing which we all do. We treat all the masses to be at the center of the sun. So basically everything is concentrated and it is a point mass. And that is an approximation we keep doing most of the time. And when we do this, then what we get is basically Newton's law of gravitation, which is basically gm by r squared is equal to mv squared by r, where v is basically the velocity, orbital velocity. Fine. Now, because the masses of the planet gets cancelled, so we get a v squared, which is nothing but gm by r. So basically, the velocity of the planet is directly proportional to the mass of the sun and is inversely proportional to the distance. Fine. And this is basically what the Kepler's third law was before he proposed this before the Einstein's before the Newton's laws. So this is basically consistent with Newton's laws. Right? And this is basically the velocity as a function of the orbital radius in terms of the astronomical unit, AU. Now you can just see that Mercury is very close to sun, and hence the distance from the sun is small, and hence naturally the velocity is larger. And that's basically what we measure. Okay. And there is some error. I have not included the error in this plot, but there is some small errors, but which we can worry about later. And similarly, if you look at Venus, Earth, Mars, and you can look at all of them, and you can actually go through this, and it'll all be consistent. So you get, and the measuring the velocity, if you measure the velocity and measure the distance, we can measure the sun. And these people are mass of the sun, and this is what people have been doing for a long time. Now, one thing which I wanted to mention, which is where many times we come in, the Neptune was as a planet was actually predicted. It was never actually observed first. It was actually predicted because of the Uranus motion of the Uranus basically told us this. I can tell you details later on, but right now I just wanted to mention that it was basically theoretically it was motivated because of the Uranus's motion, and that's how the Neptune was predicted, and then it was basically finally discovered. Okay. Okay. So now I basically kind of told us that how does the gravity actually kind of fits into the solar system. Now let us ask a question, how does it fit with the Milky Way? Because that is the next biggest object we know, which is the Milky Way. And so we can ask a question, how does the gravity behave? What does gravity tell us about the Milky Way itself? Okay. So now before I do that, actually, I just want to ask this, I want to do a very simple example so that to understand where we are heading to. So the first time when I did the calculation, we assumed that the mass of the sun was concentrated at the center and all the other planets were actually circling around, correct? Now let us take the simple example where the sun is not at the center, the mass is not concentrated, but it is evenly distributed. So basically I'm taking the sun and I'm saying that the mass of the sun, which is 10 power 33 grams, is actually evenly spread across the entire radius r. Okay, I have not fixed the radius r. We will fix the radius a little later. So we can just do this. So now let us take the case that we have actually spread the mass of the sun out to the size of the Earth's orbit. That's basically. So I'm saying that the mass of the sun is spread across the entire. Now, even now the Newton's law of gravitation is valid. But now, since it is not concentrated point mass, now we have to do the simple calculation of what is this mass of the sun that is enclosed in the Mercury's orbit. So now the mass will not be for the Mercury's orbit. If you want to do now, it is the mass enclosed within the Mercury's orbit, not the entire mass. So we have to calculate the density. If I assume the density to be uniform, so m is equal to rho times v, and v we can calculate by 4 pi 3 r cube. And if I assume that if the mass of the sun is spread out in the way that I know what is the density is, I can back calculate. So the mass is 10 power 29. So now what is happening is that I can now ask a question. So now what should be the orbital velocity of that? Okay, you might think that this is a bad example to calculate, but I'm driving down to for a specific reason. So then what it tells you is that the orbital speed of Mercury should be 10 power 4 meter per second, which is nothing but 10 kilometers per second. So this is of course smaller than this. This is because we only have a fraction of the sun's mass, which is attracting the Mercury inward. So now We can now do similar examples. Let us assume that we have assumed the density to be uniform. Now, if I assume the density to be changing continuously at a different, for instance, here in the plot A, I've given rho to be function to be 1 by r to the power of 4, rho to be 1 by r cube, rho to be constant. That's basically what I said, what I did, and rho by r cube. Now I can assume several of this thing, and like you can ask a following question: what would be the gravity, then the force acting on each of these? So if I have a mass, then if there is a planet like M2 here, then the mass will depend on how much mass is inside the galaxy, inside that star or a galaxy or the planet. And then we can calculate what is the forces experienced by the star. We can do the same thing for the galaxy now. Fine. Okay. So let me just go back. What we did is basically we have done the simple calculation for um, for our solar system. Now I want to do the simple calculation. What happens if we do it in the galaxy? So now I have a galaxy like a spiral galaxy, which is the Milky Way is. Now I want to ask a question: how do I know how much of the stars which are circling each of these arms? I want to calculate if I know the velocity. If I know the velocity of each of these stars which are circling around, how do I know what is the total mass enclosed? Fine. So we can do exactly the same calculation. We'll just do the simple calculation like what we did. So then that would give us exactly, if I measure the velocity of the stars, then it will tell me what is the mass enclosed within that star. And basically we know the distance. We can measure the distances in various ways. So we know what should be the mass of the galaxy within the radius r. So we can do this for this galaxy, and people have done this for. So what did astronomers see when they measured it? Now this is basically what happened in 1970s. Basically, Valerio Rubin was basically the main instrumental in this. These are the papers I have not mentioned. These are some 4 or 5 papers. I've just put it in together one single plot where all the figures have been put together. Now, so each of this is basically, so let me explain. What is the vertical axis is basically the velocity. So basically what we do is we look at a galaxy, we measure a star in that galaxy, we keep measuring their velocities. Okay. So you measure the velocity, which is the rotational velocity of each of the individual stars. And then we look at the distance. So you can know the distance. When I say nucleus, it's at the center. So basically we know what is the distance between this. We know what is the velocity. So from this, we can, using the Newton's law of motion, we can actually calculate what is the mass which is enclosed within that radius r, capital R. Fine. And this is the measured, what people measured. Basically, Valerio Rubin was the one who measured it. And this was basically humongous work actually. So this is basically for different galaxy. If you can see, this is NGC 4594, this is NGC 4378, NGC 250. So these are basically 7 or 8 galaxies which they measured. And all these galaxies, they found that the velocity increased and then it saturated and it went like this. Okay. Of course, you should assume that there will be error bars, but the error bars are not significant enough that it is actually very large. Right? So basically what they found is that if they plotted, in principle, if you have plotted it, as you keep going away from it, what should have happened is that since there is no mass, as we saw it in the case of the solar system, for Neptune at the 5 kilometers per second, it was very, very small. And similarly, it should be there. So if the mass was concentrated at the center of the galaxy, then what you should have seen is that the velocity of these stars, which are very far away, should have actually gone down. But they didn't see this. It never saw that. So what they saw is that the velocity was actually going almost a constant, and it got saturated and it almost to a constant for a very, very large distance. You look at the distance is basically kiloparsec. Here people haven't measured beyond kiloparsec, but I'm just telling you that this is basically the original calculation. So what the data shows is that the rotational speed of the objects do not decline as we go away from the center of the galaxy, and it actually remains a constant. So from this, what Rubin concluded is that there should be a large amount of invisible invisible or dark, invisible or dark matter that should be present. So, and if you look at the estimate, you can do the same calculation. Now you can ask a question. Now we know how many stars are there, and we can calculate what should be the mass because we know what is the this is and how does the density goes. We can make an approximation, and the thing is that out of, if it has to account for all these velocities here, then the dark matter or the invisible matter should be 90% of the galaxy mass. So for instance, if the galaxy mass is 100 kilograms, then the dark matter should actually account for 90 kilograms of it. Only 10% is accounted for stars, planets, and others. So everything else has to be, so 90% of this is basically this. Okay. So now let us ask a question. What would the, if the mass, okay, so let us go back, sorry. If the mass in the spiral galaxy were distributed like the light, like how we have seen the light, then the velocity curve of the planet should go like this, the first curve. Okay. And we would have predicted something like this. However, what we are actually predicting is that the observed velocity is actually going and flattening. So what it basically says is that since the profile is not like this, but the profile is like this, that the only possible explanation with Rubin could actually figure it out, Vera Rubin, is that there should be large dark matter or the invisible matter in this universe. So this is the code which she added in one of the papers. In a spiral galaxy, the ratio to the dark to light matter is about factor of 10. Basically, that's what I said. That's probably a good number for the ratio of our ignorance to knowledge. We are out of kindergarten, but only in about the third grade. So basically now this leads us to, so it's basically not just our galaxy, it's not some neighboring galaxy. All the spiral galaxies which they saw, they all seem to have this feature that the velocity curves, rotational velocity of the galaxies, they're all saturating as you go away from each other, as you go away from the center. Fine. So that basically leads us to two immediate questions. What is the origin of dark matter? Do we have other evidence of their existence? So I can take a quick couple of questions right now, and then I can move on to the next part. Is there any?
The first question is by Kartika Mohan. What is the exotic dark energy?
I'll come back to dark energy. Actually, I will be discussing about the dark energy later, but right now I'm talking about dark matter. So I'll discuss dark energy maybe around 40 minutes of the talk.
Yeah. The second question is by Rajeshwaran ji. I have one hypothetical question. Is dark matter is interacting us even through electromagnetic scale, but it's interacting on an electromagnetic part which we are yet to discover?
I missed the last part of the question. Sorry. They are interacting with the electromagnetic field.
I'll read out again. I have one hypothetical question. Is dark matter is interacting us even through electromagnetic scale, but it's interacting on an electromagnetic part which we are yet to discover?
Okay. Okay. So it's a very valid question. So the question is, if I'll rephrase the question. So the question is, so let us take the case that we are seeing it is if there is a dark matter, and whether it is just that we are not able to see that part of the electromagnetic spectrum which is interacting, hence we are calling it as this. Yeah, that is
Yes.
the possibility, but the point is that as you can figure it out in my first slide which I put it. Now we have looked at, we have detectors or the telescopes going from gamma rays to long wavelength radio waves. So these are all there. Okay. Now, if they have to be there, if they interact, then we should have seen some excess of light from all these. So for instance, if it cannot be from gamma rays, the reason is that it cannot be from very high energetic rays, because these are very high energy. So in order to have these energies generating, it needs a very, very difficult processes, very high energy processes. So it cannot be very, very high energy events. It has to be from long wavelength radio waves. But long wavelength radio waves, we have a very sophisticated instruments, even going up this thing where we have not been able to see anything sophisticated. So the only possibility that we have, they are interacting with some other, what is called the dark photon or a dark radiation, which people have hypothesized, and people know that it could be a possibility, but we don't know anything about it. In that sense, it is possible, but we don't know. Any other question?
Yeah. The next question is the dark matter concentrated in the center of the galaxy or spread out?
Yeah. So the thing is, what we know is that it has to be spread out. So that there is, if you, there is one black holes, there is a supermassive black holes, which is of the order of 10 power 6 kilograms, which are at the center of each of these galaxies. Okay. So if I take a galaxy now here, for instance, there is a supermassive black hole, which is present. Now, what we are talking about is basically, but this, unlike in the case of solar system, this mass is not sufficient enough to assume that as like sun is concentrated, it has to be spread out in the entire galaxy. So that is where I gave these two examples, which I gave. Sun, which is concentrated as a point particle, and then it is spread across for the entire this thing. So these two examples are important because these two are two different examples. Now, what happens in the galaxy is basically a mixture of both. You have something at the center, which is large, but you also have a very large spread out across the entire galaxy. So you cannot just keep one of them. It has to have both. Okay.
Yeah.
So can I move on now?
Yeah. How can dark matter cause the rotational velocities of the galaxies to saturate over a large distance set?
So they saturate because, so let's go. The example is basically this. So you basically, so this is your orbital speed of any planet or a star. Now, if the mass is large, then the velocity will be large. Now, so that basically so the why we are hypothesizing that there is a dark matter is because this velocity, if it would have only been light or like stars, then we know what is the mass. Then this velocity should be very small. But since the velocity is not small, so hence we are adding up. That we are adding a lot of mass. Unless otherwise we add up mass, otherwise this will not actually be satisfied. Okay.
Yeah.
So
So
just
can I
to
move on?
continue this question,
Yes.
I mean that velocity remaining constant is just observational fact. I mean,
It's an
there is
observational. Yes. So this is an
there,
observational, because of
but
which we are actually.
there
Sorry.
is nothing that is saying that the dark matter should have kept it constant.
No,
It
no,
is
no.
just that this is what is observed.
Correct. This is what is observed.
Okay.
So we know that from the observations, we measure that this is your velocity. And then we are asking what should be the mass should be added such that this much velocity is possible. Then what is actually seeing is that the mass of the dark matter should be at least 9 times or 10 times that of the normal matter. Okay. So can I move on now?
Yeah, there are two more questions.
Yeah, but can I take it later? Because I think.
Yeah, will do, sir.
Yes,
Okay, you can proceed then.
sure. Okay. So now, so we understand that by looking at by using Newton's arguments and Newton's law of gravitation, we have now an evidence that that should be dark matter, and this dark matter is there not just in our galaxy, not in few galaxies, but it is now seen in many galaxies, thousands and thousands of galaxies. People have done rotational velocity, and then all of them seem to show that this is actually the flat. So that basically means that the dark matter exists in every part of the universe. And the question is, what happens? What does this dark matter do in the cosmological scales? Fine, where the universe, when the large scale structures are there. Fine. Okay. So now, before I proceed, I just want to start with something simple so that we translate into this. So we all know Doppler effect, which we have learned it in our school. So basically, what does it tell us? It basically tells us that if let us assume that there is an ambulance which comes to us close, comes from one side, then it emits certain frequencies. Now, if we don't move, if the ambulance doesn't move, then whatever we hear and it'll be exactly the same as the source frequency, which is the frequency of the ambulance. But if this ambulance is coming close to us, then we know that it is actually there will be a blue shift, and basically that will tell us that there is going to be a change in the frequency. And this is what we know is the Doppler effect. And that basically tells us that if there is a non-zero relative velocity between the source and the observer, then we will actually get a different frequency, different from the source frequency. Fine. Now this is basically a cartoon just to explain that if I have an ambulance and we have observers here, here in all the north 4 corners, then all these 4 observers will see that the sound is propagating isotropically. That is true. The distance between the wavefronts, which they will see in all the 4 observers, will be identical. Hence, the frequency the observers will see will also be identical. Now, let us take a simple example where I am here, somebody else is somewhere sitting there, third person is sitting somewhere else, and the fourth person is sitting here, for instance. Fine. Now, what happens is, now what happens is that the ambulance is moving towards the right. Now what happens is that the distances between the wavefronts become shortened. Okay. However, on the other side, the distances becomes the wavefronts actually are longer. Hence, you see that there is actually going to be a shift. The frequency gets blue shifted here, and this becomes red shifted. When we say blue shifted, the frequency increases. When I say red shifted, its frequency decreases. But for observers here and here, nothing happens. It remains the same. Fine. And this is what we know it as a Doppler effect for the sound. Now, what people have measured, which is basically, which I'm going to show in the next slide, what people have measured is that in the case of stars and galaxies, so the stars and galaxies are very far away. Now let us take a galaxy, typical like a galaxy, like a spiral galaxy, like this, and we know that will emit some light, and most of it is all hydrogen. So everything is going to be related to hydrogen, Lyman alpha, Lyman beta, and things like that. So it will emit something, and then we can measure this. We should measure the spectrum, and we know that this is going to be this. Now, if you measure a very far away galaxy, which is what Hubble measures, very far away redshift galaxies. Now, if it measures, then what happens is that it will be, if there's a typical galaxy like a spiral galaxy like what else, then we are here. Now, what happens is that what people have seen is that the spectrum remains the same, very similar, but it is actually the frequency is lower frequency, because this is, if it is, let us take, this is some frequency which is 500 Armstrong, which is actually going to be a very low frequency, a higher wavelength. So, and this is what is referred to as a cosmological redshift. So basically what we are trying to say is that the emitted, which is basically emitted frequency of the galaxy, is not the same as the observed frequency. And what we are saying is that this is actually going to be much smaller than this. So hence we are always calling it as emitted frequency is always going to be higher than the observed frequency. And that is what is referred to as a redshift. So the expression is 1 plus z is nothing but is equal to nu emitted by nu observed, where if nu emitted and nu observed is basically identical, then z will be equal to 0. So that is basically what happens when we are in our own galaxy. But if it is a very far away galaxy, then what happens is that there will be the emitted frequency and the observed frequency will be different. Hence, there will be what is referred to as a cosmological redshift. I explained what does it mean by the redshift in the next slide. So now let us take the case. So here we are looking at different wavelengths. This is all 500 nanometers and stuff like that. Now, if it had been a nearby galaxy, then nearby star, then the redshift, this would have been, it should be, the shifting pattern is slightly different. But imagine this, if it is a very distant galaxy, then it is actually, instead of 500 nanometers, it actually becomes almost greater than 600 nanometers. So it's basically very, very far. And this is what actually Hubble saw when he measured for 10 years. So he basically did measurements for almost 10 years, 1920 to 1930. And what he basically did was he basically analyzed spectra coming from different galaxies at different distances. Okay. And he didn't know that the universe is expanding. So he never had any expectation. So he just kept measuring. Fine. So what he measured was that he measured the distance to each of these galaxies, and he measured all the different spectra, and he basically did a plot. Right? And this is basically, so on the left of your panel is basically what he did. This is this velocity as a function of distance. Please remember the distances are in megaparsec, and which is basically roughly three times the light years, and the velocity is in kilometers per second. Right now, as you can see, of course this is 1929 data which he published. Please understand that the data may not be very precise, but what he basically proved is that as the larger is the galaxy distance from the galaxies from us, the larger is the velocity in which it is going away from us, basically. And we basically saw that because of the fact that there is a redshift factor. So what he basically proposed is that velocity of the galaxy V is proportional to the distance, which is basically, so larger the distance from us, larger is the velocity. That's basically the trend which we saw. Okay, of course, you can say that this is not very good. How can you put a linear plot and stuff like that? But as a first approximation, he basically did this, and he said that V is proportional to R, and that proportionality constant is now referred to as a Hubble constant to honor him, because he basically did this thing. So all these things are basically, so R is the distance which is in megaparsec. So you don't see these things in a small distances, but in the cosmological scales you'll see. And this is basically the Rees et al., which is basically 1999 paper, because the Nobel Prize they got in 2011, which I'll tell later as well. So this is the velocity as a function of distance. Now you can see that the error bars are much smaller, and this fits the Hubble law, which is there. Now the only thing is the distances are not at 2 megaparsec. Now we are going up to 500 megaparsec. And the velocities are basically 10 to the power of 5 kilometers per second, which is basically kind of relativistic. It's very, very large, very fast, very high speed. And they're all going at very massive speed. So this is basically what the first evidence that the universe is actually expanding, and it is expanding very, very fast. Okay. So now the question is, how do we go about explaining this? Okay. Do we have a theory? Because we have Newton's theory, but the Newton's theory is not very good, because we know that the Newton's theory cannot explain, it's not very good for relativistic speeds, because as I mentioned to you already, we are looking at speeds which are like, even in this time, it is 10 power 3 into 10 power, so 10 power 6 meter per second, which is like 1/100th of a light speed of light. So it's very, very thin. So you cannot use Newton's theory of gravity. So we need a different theory. And by the time in 1915, Einstein proposed Einstein's general theory of relativity. And what Lemaître, Friedman, Robertson, Walker, they were all independent calculations, different. They were all living in different parts of the world that time. And so they had a very simple model. They call it as which is now referred to as a FLRW model. They assume that the universe is homogeneous and isotropic. When I say homogeneous, there is no preferred observer position. Observer here and the observer in a different Andromeda galaxy or another galaxy, they're all the same, and they are isotropic. So basically, when I look at a galaxy in one side and they look at a galaxy in another direction, there is nothing different about it. It's exactly the same. And this is an assumption they made. And basically, now we can actually ask a question whether this is true. And this is basically a SDSS survey, Sloan Digital Sky Survey. So this is a little old paper, but the recent ones, the figures must be much better, but at larger distance. But this is basically it. Now, this is each point, each pixel here is one galaxy. And each of them, actually, people have measured the galaxy and plotted it and put it in the sky region. And this is up to a redshift of 0.8, for instance. And these regions are not excluded because of the positioning of the telescope, because of which they cannot see certain parts of the sky, but otherwise they are able to see the entire patch of the sky. So given this, they are able to see that we can see this universe is kind of isotropic and at the largest possible scales. You may not be isotropic in the smallest possible scales, but in the largest possible scales, it's isotropic. Even now, even though the assumption is very, very simplified, but it still seemed to be a best way of going about it. So I just thought that I will put the slide just for the people who kind of know what we are talking about. So this is basically, since general relativity is a geometric theory of gravity, and it has space-time. So we write it as a space-time. So T is basically time here, which is referred to as a cosmic time. And dx is basically the 3 space. And this A of t is basically what is called the expansion factor. and the Hubble parameter h, which is basically h, which naught, which I give, which is nothing but a dot, which is basically the time derivative of a with respect to the scale factor or the expansion factor with respect to time divided by a. So a dot by a is basically h, and a dot by a at the current epoch is nothing but the h naught. That's basically what we have. Okay, so I just want to mention this. So if the universe is actually expand, then we can ask a question, what would have happened earlier, before? So now it is expanding. So what would be the universe, let us take 100,000 years ago? Okay, and this is a question which is a valid question. So now you can say that now, because it was expanding, now let us ask a question, let us go back in time. Let us take the case that I actually look at I'm going back in time and asking a question, how does the universe must have been looking like? So if it is expanding now, so it must have been expanding from a smaller region earlier. So and if you go back again and again, it would have been even more smaller. So this cartoon picture which I have taken, which basically shows this. So as you can see, as you go back in time, the radius of the universe must be shrunken. I can go back, and if it goes exactly at to some finite time t equal to 0, let us call it, and that's when the universe must have started. So this is what the predictions of Friedman, Robertson, Walker, or the standard model of cosmology is. So our universe is expanding. So when I go back, when I put the clock back in time, the universe must have been smaller. So I can go back another much more, instead of 100,000 years, 1 million year, 1 million years, and I keep going back and back and back. And it basically tells that I should have actually gone to a region which is extremely compact, and it should have been very, very small. Fine. And what we call it as Big Bang is basically this. This Big Bang tells you that it all started at some finite region, very, very small, and it expanded. And then it all started from that. Okay. Now, whatever the cause of the Big Bang, we'll come back to it much later when the question answer session. Right now, I'm not getting into it. So the physics interesting problem is, if I go back in time, if I go to a smaller region, then what it tells us is that the universe tells us it should have been actually hotter, because the temperature was hotter. Because think about it, if I had a big balloon, if I compress the entire balloon into a very small region, so what happens is that the pressure is large, everything is large, the gaseous particles will start hitting each other. So what happens is that the temperature in principle actually can be expanding, and it actually expands very, very large. It actually becomes very, very large. And that's basically, it's consistent with all observations we have. So as you go back in time, the universe was very, very hot. So even if I had a hydrogen, so this is a simple expression of a hydrogen. So even if it had been hydrogen, what happens is that these electrons, even though it would have been bound by to a proton, there is a high energetic photon. This will come and hit it, and it'll go away. So what happens is that as you go back in time, what basically the theory tells us is that the electrons are not bound to atoms anymore. The radiation and matter are actually, they just keep exchanging. E is equal to mc squared keeps happening continuously. So the photons keeps converting into itself into an electron, positron, and keeps happening. So as you go back in time, so this when we go early in time, the universe is highly ionized. At time t equal to 0, we don't know anything about it. But as you come further and further, later and later, the universe has expanded and it cooled. And then what happens is that all this hydrogen and electron combined, so proton and electron combines to form a hydrogen. And then all the high energy, all the higher elements keeps forming. Fine. So this is been pretty well done. And this is basically the 1964 paper of Peebles, for which he got a Nobel Prize in 2019, where he said it is a possible thermal history of the universe, when he said the universe was actually highly ionized at very, very early time. And then as the temperature cooled down, then the matter, the radiation became very, very small, and we had a matter dominated epoch. And that's basically what is called the matter. And this is consisting of electrons, helium and other things, protons and stuff. And that's basically what is it. There was no dark energy at that time. So he didn't have any mentioning of dark energy here. And this basically is now the blueprint of what the universe possibly evolved from a time t equal to 0 to current time, basically. Fine. So the basic idea is that when you go back in time, the universe was very, very hot. But now let us ask a question. Let us now proceed forward from the Big Bang. Let us assume that we don't know anything about Big Bang. Let us not worry about it. After the Big Bang and after a few seconds or so, we kind of understand how the universe must have happened, what happened. So it went through different stages in the universe. It went through a radiation dominated, it's where everything was radiation, everything was like photons, electromagnetic fields and things like that. And after that, when the system cooled, when the universe cooled, then most of it became hydrogen, helium, and other forms. And then there is all these things formed, and basically it became a very matter dominated, and now what is called the dark energy dominated. I'll come back to it later. But this is the clear prediction of the Big Bang model. And it also basically, since there is radiation and matter were actually interacting with each other. Once at some point, when the equality was, when it became transparent, when the universe became transparent to light, then whatever was the interaction, everything stopped. And that basically, there should be a remnant of this radiation, and that is what is called the cosmic microwave background radiation. And that basically what people have seen. First, it was Penzias and Wilson, which we saw using the radio telescope, which basically showed that there was this thing, and this was basically this. It was in 1965. This was the first evidence of Big Bang, and that led to the Nobel Prize in 1978. And after that, people have now measured Kobe measured in 1990, and then now there is a WMAP, and then there is several other experiments which have been measuring, and all of them basically tells that they're all perfectly well predictions are. These are the predictions of FRW background. I can take a pause and I'll take questions, and then I can go ahead with the rest if there are questions.
Yeah, there are so many questions.
Yes. Yeah.
The first question is, have we figured the properties of dark matter, like Pauli's neutrino hypothesis, which predicts the properties of neutrino before it was detected?
So the properties of the dark matter. Okay, so I think this links to the another question which they asked, that it could be a electromagnetic, it could be another form of electromagnetic. So basically, what people the one thing which we have to know is that all forms of matter, irrespective of whether it is dark matter, dark energy, or any form of it, all of them interact with gravity because they all have energy. According to Einstein's theory, any form of energy will contribute to gravity. So they all contribute to gravity. So the only way we measure them is by using gravity. Basically, as I said, V squared of R is nothing but GM of R by R. So then the question is, how do we distinguish whether this is dark matter and this is dark energy? That is a slightly different question itself. Now, what I wanted to mention is that the only way which we know that dark matter exists is basically through, first, with this basically saying that there should be excess mass, and this mass can only interact with gravity because that is, every mass has to interact with gravity. But we don't have any other way in which they interact with electromagnetic or any other form of force. Does it answer the question? I don't know.
Yeah. The next question is, how likely is it for the alternate theory to dark matter, such as modified Newtonian dynamics, to be correct?
Okay, I'll come back to the MOND when I discuss about that at the end of the dark matter discussion. Which I will take it in the next 10 minutes or so. Then I'll come back to MOND. I'll mention it in the slide. Yes.
Is it dark matter versus modified gravity theory when we talk about galaxies? Can we say it is not dark matter, but gravity is changing its definition?
Okay, I will take this question also along with the MOND. Actually, I'll take the distinguishing between MOND and this. I'll come back to it when I discuss the dark matter a little more. Yeah.
So what does the dark matter consist of in the basic level? Is it present in the same amount as it was at the beginning? How does time affect it?
Okay, so the thing is, so let us, so this may be something to mention. So as I mentioned, when the universe expands, everything, as it cools down, the density also cools down. So the masses, So the way we think about it, it's like we are sitting inside a vacuum chamber, and there is no exchange of there is no exchange of energy or masses. There is only this thing. So let us take the case. I remove the piston from it. The number of atoms are actually going to be the same, because the piston is just moving up. Okay, if I move the piston down or up, the number of atoms or the gaseous particles is in the piston is going to remain the same, except that the density is going to be different. The temperature will decrease and or increase depending on whether I'm pushing it down or not. So here also the number of dark matter particles or the baryons will all remain the same, except that the density is going to decrease as a function of time. As it expands, the density is going to decrease.
Yes. The next question is, do dark matter interact with itself? Can they form a star, planet, or even black hole as they respect gravity?
Yes, so they can form everything, but the only thing is the problem with the dark matter, the way we envisage dark matter, is that it doesn't interact with light. So we cannot see them interacting with light. So we cannot use the electromagnetic telescopes, radio, or normal telescopes, or UV, or gamma rays, X-rays. No, we cannot. With that, we will not be able to do it because they don't interact. So hence, so all these conjectures are there. People actually have been conjecturing about it, but we don't know what properties. If you ask me a question, we know what is electron, what is the mass of an electron. We know what is the charge of an electron. We know what are the properties of it, because electron interacts with electromagnetic light, and we can actually measure certain properties. But since they don't interact with electromagnetic fields, then we will not be able to make any sense of the property. So all these things are possible. There could be exotic stars, there could be exotic black hole formation. Everything is possible, but we don't know how do we test them.
The question is, do we have a mathematical proof of Big Bang?
What do you mean by I don't know whether there is a mathematical proof? We have a experimental evidence. We have a mathematical equation which predicts the Big Bang, but we don't know exactly what happened at t equal to 0.
Yeah, regarding the last but one slide, sir, from where did it start? How small was it, and how high was the temperature? Is there
Okay,
any
so
way?
the
Is there a
temperature
way
is
to test it?
okay. So we have various ways of testing it, because the CMB, which actually I'm going to mention it in the next slide or so, I will mention this. So from the CMB, which is a cosmic microwave background, temperature fluctuations of the cosmic microwave background, we have a lot of understanding of the within the first. So Big Bang happened at t equal to 0. So we know from t equal to 10 to the power of minus 10 seconds onwards, till what happened right now, we have a fairly decent understanding. Okay. Is that okay?
Yeah, last but one question. Is dark energy kind of negative energy?
Dark energy, I'll come back to it. I'm not discussing dark energy right now. I'll discuss dark energy in the next 10 minutes.
And one more is it possible to observe CMB but for neutrinos?
Observe CMB. So the thing is, neutrinos are basically so the interaction of neutrinos with CMB with electromagnetic is very weak. So it is even weaker. So we will not be able to measure them through the interaction. We will be using them, for instance, when there is a supernova burst, we will see neutrinos, and that would give us some signature about it. But you are asking a question whether that will interact with the electromagnetic, and from that, no, that would be very weak. You will not be able to measure it.
Okay, complete your slides and then there will be questions. There are few hands also.
Okay, fine. Okay. So I basically kind of gave a view of what are the success of Big Bang. Now, the Big Bang model comes at a price. So as I mentioned in the first slide of the presentation, we have our current understanding of the universe demands that the dark energy, which is 70%, dark matter, which I explained a lot, which is 25%, and the matter, which is basically radiation, stars, galaxies, everything that puts together 5%. So basically, we don't understand 95% of the universe. That's kind of thing which we have to understand. Okay. So now let us go back to the details. So what is the matter? So the matter which I'm saying is atomic matter, basically, which is the calendar, which is the Mendeleev table, which we have, all of them, which will be considering as atomic matter, and they takes up 5%. Protons, neutrons form the nuclei, and then the radiation, basically CMB, neutrinos, everything goes into the radiation. Now, the problem which people have not understood is that at the early universe, field theory or quantum field theory, particle physics tells us there should be equal number of matter and antimatter. But then the question is why there is no antimatter. We don't see very, very, very negligible antimatter exist, if at all it exists. So why there is no antimatter? So this is a puzzle which Big Bang cannot answer. Particle physics has to give an answer to this. So I will not get into this, but it's an interesting question to go ahead. Now, the next problem is basically the dark matter, which is what I spend most of my time right now. It consists of 25% of the universe, matter that does not interact with light. So the dark matter dominates the galaxy mass, as I mentioned in the previous slides. And we have no information what it is made up of, where it comes from, what was the origin of it, and things like that. Nothing is known. And the next, which is what I have been not answering, which I will answer in the next 2 slides or so. So now the thing is the dark energy, which is basically forms the majority of the universe energy density. It is responsible for the accelerated expansion. And we also have no idea about what this meant. Okay. So now comes in basically, this is basically the Planck telescope satellite, which has basically measured the cosmic microwave background fluctuations. So basically, the Big Bang tells that there should be a cosmic microwave background, and the temperature of that should be of the order of 2.7 Kelvin, right? Now, what people have said is that there could be fluctuations in this. And these fluctuations, if we can measure it, then that would actually tell us various things about that. So what these telescopes actually measured is fluctuations of the order of 10 power minus 5. So that is T, that is delta T, which is the change in the temperature divided by the mean temperature, which is 2.3. So delta T by T is of the order of 10 power minus 5. So that basically tells us that what are how these fluctuations are. And this measurement of these fluctuations actually gave us a lot of information about how the universe is made up of. And that's how we know very clearly that this is how it is. And this actually, if this should have been formed, then that also indicates that dark matter should exist, because the way to think about it is that the galaxies and the galaxies could not have formed if there is not enough dark matter. The reason is that dark matter doesn't interact with light. The electromagnetic fields, electromagnetic particles, when they interact with another electromagnetic field, there is something called a shielding, which basically cuts off all the potential, which is be 1 over r. It becomes an exponential of r. So hence you cannot be able to attract. So in order to attract them, the only way it can be attracted, because dark matter doesn't interact with electromagnetic field, then it has to be dark matter, and that basically forms. So the dark matter is I can show you the slides a little later, where they have done simulations and they show that this can actually be retrieved in a computer if you run the simulations without a dark matter and with the dark matter. So what is the properties of dark matter? And we know that the universe is living for 14 billion years. So it should be actually a stable particle, which should be at least be 14 billion years. And it should not interact with other forms of matter except for gravity. As I mentioned, every form of matter should interact with gravity. So this doesn't interact with any other matter. So it should be interacting with gravity. It should be produced in large numbers in the early universe. It could be axions, it could be WIMPs, it could be neutrinos, it could be primordial black holes. We have no information. So all these possibilities exist. Okay. And we hope that in the next 15 to 20 years, in the concluding slide, I'll mention that we should hopefully get some information about it. So currently, all these are possibilities. Okay. So now let us go back to the question about what is dark energy. Okay. So now I'll go back to the container. So I have a box of this container and I have a piston, for instance. Now what happens is that we know that this is basically the pressure on the container is coming because of the collisions, right? These particles, the gaseous particles will come and hit the walls of the container, And then that would actually be giving pressure, and there will be a Newton's third law tells you that there will be equal and opposite reaction. So hence there is actually a pressure difference which happens, right? Then that's basically see the pressure. Now, if I increase the number of gas particles, the number of collisions will increase, automatically the pressure increases. That's basically what happens in the normal matter, like in our day-to-day lab, that's what we see. Now, the problem is the dark energy, as we envisage right now, is actually has a negative pressure. So the energy can never be negative. Energy has to be positive. So energy is positive for this, or the energy density is also positive there. But the negative pressure is negative. So what basically means that if we increase the number of dark energy molecules, the pressure decreases. So it is opposite of what we have actually understood. So what I'm saying is here what happens if I increase the number of molecules here, we know that the pressure will increase. So for instance, if I keep balloon, put a balloon, if I blow the air into the balloon, after some point the balloon bursts. That is because we have increased the pressure so much that it will burst. So it's exactly in the same way. Now, if I keep increasing the number of dark energy molecules, so let us assume that I have a container, I have a very hypothetical container, and I'm pouring in lot and lot of dark energy particles. Now, what happens is that this dark energy particle is such that it's so mysterious that if I keep increasing it, the pressure decreases. It's opposite of what we have actually done in the lab. So unlike the matter, the total energy in the dark energy is proportional to the volume. So as the universe expands, its total energy increases. So it's actually weird. It's even weirder than what we actually know. So what happens is that as you keep putting in, so what happens is that in the small distances, it doesn't play a role, but in the larger distances, it tends to accelerate objects and pulling up, it opposing the pull of gravity. And this is exactly what people Rees et al. Measured in 1997, 1998, and which led to the Nobel Prize in 2011. So this is basically the plot of luminosity distance as a function of redshift of supernova. So basically what they did is they kept measuring supernova at very large distances. And this is basically distances up to redshift of 1 and 1.2. So don't take the beyond 1.2 seriously, because sometimes there is a lot of errors in the. So what they said is that if they did it, the only way it will fit the model is when there is a dark matter. So this is basically for 3 plots: green, red, and blue. Now, if you look at blue, where there is no dark energy, that is omega lambda. Lambda is usually referred to as dark energy. When there is no lambda and there is only matter, then this will not fit any of these plots. Most of the plots will not. Most of the supernova will not be fitted. But if you take only dark energy and there is no dark matter, that also will not fit. The only time it will fit is when there is a 69% or 70% of dark energy and the rest of it is actually matter. And that would fit exactly this inside. And this actually has been verified by the cosmic microwave background, WMAP, as well as Planck. And this verifies that there is actually dark energy which exists. Okay, so I will take some questions right now before I go to the last part of the talk.
The time is already.
It's already done? Oh, okay.
Yeah. You can
We'll continue, sir. Sir, we'll continue for 15 minutes.
Okay. So if there is any question, because I will take it up. And
yeah,
then
question we'll take afterwards.
You want me to take afterward? Okay, good. Very good. Okay. So now, as I mentioned, so the standard model of cosmology, which is the FLRW spacetime, so FLRW cosmology, is actually a pretty good, but it has its own problems. The problems are that it cannot explain what is dark matter. It doesn't explain what is dark energy, and we are just adding them up to explain something, but it doesn't actually give us a clear understanding from fundamental principles. Now, the problem has actually even more severe in the last 7 to 8 years. So people have been trying to measure this Hubble constant for many years. Okay, and this has been going on starting from Hubble itself, and then going on now with very high sophisticated technological instruments. They have been able to measure. So this is basically a plot of various measurements which people have done till 2020. As you can see, different instruments, the error bars are actually reducing, and now we are actually converging. Okay, and we thought that we are actually converging to a particular value. But what has happened is that two sets of experiments, two sets of observations is giving us two different values. So for instance, the Planck measurement, which I've given on the top, tells us that the Hubble constant is 67.4 kilometer per second per megaparsec. But the supernova and SHOES experiment, which is basically all these blue colored plots, they seem to suggest it's of the order of 75. Okay. So there is a 5 sigma deviation between the CMB measurements of Planck and the SHOES experiment and other experiments which are there. So these are going to give us two different levels of experiment, two different values. So there are what is called the local measurements and cosmic measurements. So these are basically measurements tells you around 74 and 75, while the CMB measurement gives us 67. Okay. Now the way to think about it is the following. Let us assume that we have a car and we are driving at a constant speed, and the speedometer is showing always 74 kilometers per second. Correct. Now you stop the car and you calculate the total distance and you divide the time. And if you take that, and that tells you 67 kilometers per second. So these are the two ways of thinking about it. So one kind of measurement with the speedometer, it tells you 74. But if you take the total distance and you measure, and you take the total time you take, and you divide that, it is giving you 67. So these are actually not within the error, but they're away from the error. So the only way people have been looking at either speedometer, the current speedometer which you are doing is actually faulty, or the odometer or the clock may be faulty. So people are actually trying to explore what is the cause of this. So the discrepancy between the local measurements and this thing is 5 sigma, as I mentioned. Now the way to think about 5 sigma is if you toss a die, and let us take the case, you keep tossing it and you have got the same number, for instance, 8 times continuously, and ask a question, what is the probability of getting 4 8 times? That is 1 by 6 to the power of 8, and that is like 10 to the power of minus 8 or 10 to the power of minus 9. So the probability that you do the dice and you get 4 every consecutive 8 times, its probability is very low. And that is basically a 5 sigma deviation. So what people have now think that this is actually a very, very clear, proper thing, that it is actually a problem. And this is what is referred to as a crisis. Okay. So now, please remember, all these measurements are done using electromagnetic. Now think about it as we have been having only one eye, and we have a binocular vision, right? As a human, we have a binocular vision. Let us assume that we had only one eye and we measured it. So we will not be able to see the depth, because the second eye is actually helping us to have a visualization of the universe in 3D. That's what we do right now. So now we can ask the following question. Now that we are able to discover, we know that gravitational waves exist, and we know that they also carry energy and they have similar properties like electromagnetic waves. Now, whether we can actually measure them with using the gravitational waves, can we actually get some more information about the universe? And that's basically what people are looking at. Now, the interesting thing about gravitational waves, unlike in the case of electromagnetic, we don't measure their energy. We measure the distance they separate. So for instance, it's like a Hooke's law. We only look at, we know the length, we know what is the change in the length, which when we put the pressure, when we apply some stretching or pressure or force we apply, and we only look at it. So, and then we look at how does it produce, how much change it produces. So that we measure the change in the strain, which is delta L by L, and which is basically Hooke's gravitational wave obeys something like a Hooke's law. So since even though the energy goes as 1 by r to the power of 4, the amplitude goes as 1 over r. So think about it. So if I go to a farther distance, the amplitude will go by 1 by 2, but the energy will go as 1 by 4. So basically, we are actually gaining a larger, when we use gravitational waves, we actually can go to farther and farther distances. And that's basically what people are doing. For instance, Einstein telescope. This is basically a cartoon from the Einstein telescope website. As they see, the current LIGO is only able to go to Z is equal to 2. But with the sensitivity slightly lower, higher sensitivity, they are able to go now. For instance, the Einstein telescope will be able to go to up to a redshift of 100, which is a very, very large redshift. So basically, in the next 10 years, what we are actually going to see is that we are going to see an enormous number of information coming from very high redshift. universe. Right now, we are not. So we have one event, which is the binary neutron star event, which is GW 170817, and where one could actually see both the electromagnetic and the gravitational wave signal. Both of them were actually able to see. And this measurement was able to provide an independent estimate of the Hubble constant. But the problem with this was that this value was exactly at the center. So for instance, this is a curve of probability of H0 as a function of H0. Now, as you can see, the blue curve here, which is basically what the gravitational wave predicted, and the orange one is basically what the Schu's measurement or the local measurements are, and the blue curve is basically what the Planck measurements are. Now, this sits exactly at the center. But please remember, the error bar is large. Now, in the next decade, we will have a much better instruments, much more and more events. We are hoping that this curve which we have should be shrunk, and we should be able to precisely measure the H0 precisely. Okay, so now that I have basically said what are the things and what are the thing, what is the next decade or the next 2 decades is going to tell, because that is what is relevant for most of you. So as I mentioned, we don't know anything about dark energy. We don't know anything about dark matter. We have some understanding of how the initial structures form, but with the JWST and other observations, we have to rethink about some of these initial structures, how they formed and things like that. How did the supermassive black holes in the center of the galaxies were formed? What is the origin of the magnetic field, which I didn't mention, and what causes the variations? So these are basically the open questions which are there. And so this is basically a snapshot of a page from the Mega Science Indian missions, which Indian government has approved. And these are basically going to be operational in the next 10 to 15 years. And you can see in different categories: optical IR, solar, radio, gravitational waves, neutrino as well. They are there. So all these are actually going to looking at data coming from all of this. So some of these research projects are going to produce petabytes of data daily, which is equivalent to 500 billion pages of standard print text. Now, so definitely there is going to be advanced computational methods which are necessary, because these, please imagine, one day we are going to produce petabytes of data. For instance, Sky is going to produce that much amount of data. LIGO India will produce that much data. ET will produce that much. Everything else, all these other this thing. So we need advanced computational techniques, which is going to be the next set of things which are required, because these not just amount of data, but we also need to get these data very fast. Okay, but that is one part of the story. But the next part of the story, which is basically where it's a theoretician's paradise like me, for instance, we can ask the following question: what stories or what stories does this data tell us about the universe, and what new phenomena can help us understand? So I'm sorry, actually it was cut. What new phenomena it helps us to understand the universe? So the explanation of new and unresolved astronomical cosmological phenomena are there, and that is basically what the next 10 years or 15 years are actually going to undergo. I'll stop at this. I can take questions.
Yes, there are 3 questions.
Yeah.
Can you please tell about cosmological constant paradox?
Okay. So I will talk about the cosmological constant as the case of dark energy. So there are one thing is basically the paradox itself is basically what kind of matter can have a negative pressure. Okay? We have all witnessed positive pressure. We can also have zero pressure environment situation. But what is the negative pressure, and what is this kind of fluid which can have such negative pressure? So that is a paradox which people don't understand, and hopefully we will try to understand in the next few. So another possibility is, both for dark energy and both for dark matter, is there could be a possibility that these are because we have very little understanding of gravity. So the gravity itself is behaving differently. And so I think there was a question which was asked. So people have been looking at whether the dark energy is because we don't see, we have not measured precisely Einstein's theory, tested Einstein's theory beyond solar system scale. So maybe in the galactic scale, there is a other kind of gravity terms which are to be present and which you have not included. And that is one model which is called MOND, MOND, modified Newtonian dynamics. And people have been trying to do that. But the problem with MOND is that it could explain the galactic rotation curves in the galaxy. But if I extrapolate that to a cosmological scales, then it fails because the cold dark matter, which is basically the good model, could explain the dark age structure, all those stuff, but MOND cannot explain it. It also has a problem with weak lensing measurements. So hence, the MOND theory itself is having a problem. But similarly, you can also ask a question, if it is not dark energy, but it could be a modified gravity at the larger scales. People have been trying to construct, but still, I think this is at infancy. We still have a lot of things.
Yeah, the next question is, what do you mean by temperature of radiation?
Okay, so the temperature of radiation is basically, I can associate. So as I mentioned, we can measure the energy. Okay, now we have an energy corresponding to any system. So I'm sitting in this room, and the temperature of this room is, let us take 28 degrees centigrade. And I know what is the corresponding energy, which is for each molecule, which we know it is nothing but equal to E is equal to 3 by 2 kBT, for instance. Right? Now you can ask a question. You can ask the same question for a radiation. If it is enclosed in an environment, what should be the corresponding energy or the equivalent temperature for that? Which is basically again, we can equate the energy of the radiation equal to 3 kb times T, and we can say equivalent temperature.
Yeah, the next question is, do we have a theoretical or mathematical relation between dark energy and dark matter?
So there is a difference that dark matter and dark energy are not the same things. There could be, they are, at least the way we understand it, we have two different, they are working in two different scales. Dark energy, we see it in the galactic scales. Dark matter, sorry. Dark matter, we see this in the galactic scales, but the dark energy effect can only be seen in the cosmological scales. So in that sense, they cannot be of same origin.
Uh, the question is dark energy affected by the increasing entropy of the universe?
Can you repeat? Sorry.
Is the dark energy affected by the increasing entropy of the universe?
Oh, okay. So I don't know which entropy which the person was asking, but I think uh, entropy, if you think about in thermodynamics, the entropy is basically one part of the energy which cannot be used. Okay. Okay. So this cannot be due to entropy. It could be due to some other, people have been thinking about what is called entanglement entropy and things, but not the thermodynamic entropy, at least.
Yeah, there is one more question asked by Parth. A very characteristic property is its light mass ratio. But with dark matter, how do you measure this parameter with so much uncertainty about the amount of dark matter? Also, the percentage of dark matter is variable in galaxies. So how do you categorize the amount of dark matter in galaxy and true mass light ratio?
Okay.
Also, what is the amount of error that we get from such measurement?
Okay, I kind of understand. Okay, so the way to think about it is the following. So what we do is that we 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 have this plot. For instance, let us take NGC 4594. So let's take this. So what we do is we don't know anything about dark matter. We first agree to that. Now what we know is that we know the number of amount of light we receive in a given region from a galaxy, and then we use the light to mass ratio as you mentioned. So we know what should be the total mass content within that region. Okay, with some error bar, of course. Now we use that mass, and then there is another mass which is coming from the dark matter, which we don't know. But then the question is that even if this mass is only 10%, so even the error is very small, even if the error is large, it doesn't matter because the mass contribution by the other one, which is unknown, is very large. So hence, we know that it is precisely this amount of mass is required. So there is such a large amount of dark matter mass is required to explain this. I hope it clarifies his question. I don't know. I answered it slightly more
We
non-trivial.
take
But
this last question now. Can we plot dark matter distribution curve of galaxy or a bigger structure?
okay. See, we don't know the dark matter distribution. We can only so we kind of will do it if you do this what is called the gravitational lensing. Should in principle give us some information about it. But I think I am not an expert in this, so I will not be able to mention. So there is something called a weak lensing measurement, which should be actually be able to do this.
And there is one hand raised by Palusa.
Yeah, I have
Can
been
you
seeing
unmute
this
and
hand raise
ask?
for a long time. I have been seeing this hand raise for a long time.
Yeah, I think by mistake or something.
Sure. Okay.
Okay.
I
Thank
think
you, sir. We'll be
Hello,
starting.
sir.
Yeah, you can ask your question.
Okay. Hello, sir. Good evening, sir.
Yeah, good evening.
I have two questions. One is related to the dark matter distribution. As you said, we can do it with the help of gravitational lensing. Can we do it like inside a galaxy with the help of the rotational velocities of the stars? Can we determine the distribution of the dark matter?
No. So the weak lensing measurements are only done for the cosmological part, not in the galaxy.
Not like with the help of the lensing, but with the help of the rotational velocities from a star, nearby stars, and all those.
Uh, uh, can you repeat the question? Because
Okay.
I got confused about the
Okay.
missing part.
As the Vera Rubin has said, as you go outer to the galaxy, outer parts of the galaxy, the rotational curve gets saturated, right?
Correct.
So, based on the same principle, by calculating the rotational curves of the stars, can we determine the distribution of dark matter in a galaxy?
So okay. See, the thing is, the current assumption we make about the galaxy, about the dark matter, is that it's uniformly distributed. So
Okay.
because that is the simplest assumption we can make.
Okay.
But the reason is that we don't know anything about the properties, because we don't know anything how they interact. So there is a lot of uncertainty in the way we only can do only about the mass. We should know that within this radius, this much mass should exist.
Okay.
That's the only thing. See, think about it like this. So let us take from afar. My camera cannot recognize anything, but it will only tell that I will only be able to know what should be the mass. I will not be able to from the characteristic. I will only be able to know what is the mass. It will not be my camera cannot distinguish anything else.
Okay, sir.
Okay.
Yeah. And the other question is, sir, about the redshift one. When we say as a galaxy is at distance rate, it has a very high redshift, right? So, can this redshift be not just because of the expansion or like it is, moving away from us, but can it also be because of its interaction with the intergalactic medium that is present in that?
Yeah, but intergalactic medium is again could be composed of the dark matter itself. Why
No,
should
no,
why should the dark matter only be in the galaxy?
no. This is not related to the dark matter thing. This is like a different question. So when you say that a galaxy that is at a distance of so millions of years, what is the certainty or what is the reliability that you say it is exactly at this distance just based on the redshift? Can't the
Okay, so
redshift be?
okay. So let me just go back to that. Okay, so I'll explain this. Okay. So what happens is that the galaxies are not just emitting one light. We
Mhm.
not just see only one. We see emission of not just one, but we see emission of many such lights, many such. Not just this, we could also 1, 2, 3, 4, maybe many of them. And we actually look at each and every of these spectra, and we match it with whatever we know from the laboratory. And then we take an average of it, and then we get the precise.
Okay. Okay.
Not just by looking at one data point, but we measure it with different.
Okay. Okay.
So like here, a galaxy will emit not just one, but it will emit many.
Yes.
And we will look at, that's how we will actually measure, because we will look at each and everything compared to it which original, and then we do a kind of fit it with, because the spectra is, lot of spectra can be possible, right? So you have to go back one by one.
Okay. Okay. Okay.
Okay.
Understood.
Then we
Okay,
know
sir.
precise. Then we know precise.
Okay. Thank you, sir.
Okay.
Sir, we'll,
Any
There's
other?
one more hand
we'll
raise is
pass
there,
on
but
other
time is
questions.
Mahesh.
Yeah, so we'll pass on these questions to sir, and his answers can be shared on the group later.
Sure.
Okay.
So thank you, sir. We'll be starting with a new session.
Okay, fine.
That is our valedictory session. And
Okay.
you'll be there for that session also.
I'll be there for that session now. Okay.
Sir, you are our guest.
You are the guest of honor.
Sure. I've stopped sharing.
Sure. So every good thing has an end, and today is the valedictory session now.
Sir, I will just a minute. I will stop this recording and start a new one.
Okay.